Hi, I am a PhD at the MPIA, and I will be showing you the effect of dark energy on galactic scales. So my supervisor is Andrea Macciò, also at the MPIA. We also work with Greg Stinson and Luciano Casarini. So, as I'm sure you all know, today more than 70% of the whole energy content of the universe is in a form of dark energy or a cosmological constant. And you can choose that. You describe it with a cosmological constant, so that means that you are assuming that the whole universe is permeated with a homogeneous fluid whose equational state parameter W, so its pressure over its density, is equal to -1 at all time. You can drop the assumption, and you can allow W to be a function of redshift. If you went to the talk this morning about dark energy, you will know that there are some reasons why you would want to do that, but I'm not going to go into that. So for this project, the models that we are looking at are basically the simplest dark energy models that you could extend from lambda CDM. So we have 3 models that describe W with a linear parameterization as a function of the expansion factor. So you have 2 constants, W0 and WA, that change for all these 3 models. And then we have a 4th model that instead describes dark energy with a scalar field that is a function of the scale factor, and the scalar field has a Sugra potential. But despite of the models, the point is that all the evolutions of the equational state parameter are consistent with the data. So here I plot the I overplot where the models lie in the 2 sigma contour from the WA and W0 plot from WMAP 9. And you can see, of course, lambda CDM, -1 and 0. And then we have the 4 models that I'll be talking about. So these are the evolutions of the equational state parameter. So again, in black, lambda CDM constant to -1. And then there are some models that come from above and some models that come from below -1. So what does this mean? If we allow W to be a function of redshift, what we are changing is basically the evolution of the background. So here, the Hubble function, so A dot of A. This will be the Hubble function in a lambda Kodak matter model. So you have the standard component for matter, radiation, and then a constant contribution from a cosmological constant. But if we allow this contribution to vary, then we have to take into account its evolution. So to just give an idea of, in physical quantities, what this means is that you will have, for instance, different expansion velocities for the different models of the universe. So again, in black, lambda CDM, and then, for instance, the blue line, so the Sugra model, will have an expansion of the universe that will always be faster than lambda CDM throughout its evolution. Instead, the yellow model, for most of its evolution, will expand slower compared to lambda CDM. So since I produce the initial conditions so that they all have the same sigma A at redshift 0, that means that if you have a model, for instance, the blue one, that has a faster expansion, it has to start forming structure early in order to compensate for the expansion of the universe and to arrive today with the same sigma A. Of course, the yellow model instead will have to start forming structure later in order not to produce too much at redshift 0. So the backgrounds of these models do change. There are differences. But on the other hand, if I run a zoom-in dark matter-only simulation of a halo that is 8 times 10 to the 11 solar masses, and we look at the density profile as a function of radio and the rotation curves for all the cosmological models. So again, it's the same initial conditions. It's just changing the cosmology. We're basically seeing that there's not a big difference, and we definitely cannot distinguish between the cosmological models with observations, for instance. And there has been literature on this. There's been people running dark matter-only simulations with dynamical dark energy models. And then later on, people have also introduced baryons in these simulations. But mostly, people have been looking at cluster scales, because it's true, that's the scale where dark energy is most effective. But the point of this talk is to show you that it's not only cluster scales. And if you look at galaxy scales, then it becomes important as well. So the idea is to add the dark to the dark MaGICC project. So I will be keeping the same recipe for feedback fixed. So as Aaron explained it, there's a supernova and et cetera, et cetera. But the point is that whatever the recipes are, they're fixed. And I only change the background, and I only change the dark energy. So it's not really important, like the single results, but more the relative changes accord with the different cosmologies. So at Redshift 0, these I will plot the results here. So this is again the same plot that you've seen in Aaron's talk, stellar mass as a function of halo mass. And this is where we expect the galaxies to lie from abundance matching. And this is, of course, Redshift 0. So I have been working with 3 halos so far, so 3, 7, 8 times 10 to the 11 solar masses. These are the lambda CDM simulations. And so for each of these halos, I have run all the other cosmology models. So for instance, this is the fastest expansion of the universe model. Then we have the yellow model that has this lowest expansion, and then blue and green lie in the middle. So first of all, it's quite interesting to notice that the trend in the cosmology is maintained in all 3 galaxies. And, but even more interesting is that the change in the mass of dark matter is quite small. Is around, like, OK, depends on the galaxy, but around 3% of the total mass. And instead, the change in the stellar mass becomes big. And you can even double the mass in the stellar mass, going from the yellow to the blue. So even more interesting is to look at the time evolution of the star formation rate. And here I only plotted the 2 most extreme models, just out of clarity. And this is one of the 3 galaxies that I was talking about, so 8 times 10 to the 11 solar masses. And there's a big difference. So it's clear that once you add baryons, that these help you to distinguish the different cosmological models in different dark energy models. So it does what we expected. We expected the blue model to start forming structure earlier, it does produce more stars. And the yellow model, instead, it's interesting to see how it's the dark energy that we put in to this model is able to suppress and delay star formation up to very, very recent times. So there's clearly differences. And these can also be seen in the rotation curves. So this is Redshift 0, same galaxy, 8 times 10 to the 11. And that's the circular velocity as a function of radius. And basically, we're able to flatten rotation curves only by changing the dark energy, which is quite a result. And what is even more interesting is that the degree that we are able to change this is basically comparable with the degree that you're able to change rotation curves, changing the details in the feedback. So here's a plot by Stinson et al. From the MaGICC project. So apart from what the details are in the feedback recipes, that's not really the point. The point is that the change in the rotation curves is actually comparable to the change in rotation curves that we get by only changing dark energy. So why is this happening? Well, as I said, the blue model starts forming structure earlier. So it starts with a slightly bigger potential wall. That is definitely not enough to justify the big difference that we have in the stellar mass. But the point is that once it starts making a little more star, then of course it makes more metals. And the metals help the cooling, so the cooling time decreases. And this will in turn form more stars. And basically this loop helps differentiating between the models. And here is the metallicity in internal units as a function of the physical time in gigayears. And you can see that the blue model definitely has a very different trend compared to the yellow model. So we can notice that also in these movies. So here the baryons are color-coded with metallicity. And you can clearly see the delay in the accretion histories. So you see, for instance, this arrives into the center earlier than lambda CDM than the yellow model. But also the reactions are different because in a second we will see that there's more metallicity after this merger in the, there we go. So there's more red in the blue model compared to the lambda CDM and to the yellow model. So this is, quite some difference that were not expected. And to conclude, I would just like you to First of all, remember that dark energy does matter on galactic scales, and that when you run galaxy simulations, you are making some assumptions, and those assumptions are not negligible. You're choosing a cosmology, and that is going to affect your redshift 0 galaxies, or actually throughout the whole redshift. The second point that I showed you is that baryons actually matter a lot. And they enhance the differences between the different dark energy models, because when we looked at dark matter only simulations, basically there was not much of a change. But by adding baryons, we get really different trends in star formation and rotation curves and so on. And what is also to keep in mind is that, of course, feedback is what you need to make realistic galaxies. There's no way out of that. But how you actually model your feedback recipes, how you choose the details, produces effects that are actually comparable to how you choose to model your dark energies. So that's, and if you, okay, the paper will be out soon, and yeah, thank you. Thank you for the attention.
Well, I'll start. So very interesting. You made the statement at one point that this potentially provides more cosmological information. And I guess isn't it really more fair to say that your conclusions about feedback are going to depend on the dark energy constraints? I mean, do you ever think that we're going to understand feedback enough?
No, I don't think that at the point we can disentangle between the two effects, yes. But yeah, I just wanted to underline that they're both important. That was
totally agree. Okay. Another question?
So, I guess at one point you did show that this was done at 2 different mass scales. I'm just wondering how much these effects are really systematic as you vary the cosmology versus, a small difference in the merger history causing some big nonlinear difference with feedback.
Well, okay, it's true that I only have 3 galaxies, but in all 3 of them, just 1 second. So I wouldn't get the trends to be reproduced if it was, don't you think? I mean, I wouldn't get in all 3 models, all the cosmological, the blue model always makes the galaxy lie on top. I wouldn't get, okay, it's true, I can.
I mean, I guess it's fair to say that all galaxies form earlier in
I
this model, but they're still scattered.
Yeah, I'm just